Welcome everybody. I am Teacher Park, the master student in the real-time ubiquitous system lab in Seoul National University in South Korea. I'm introduced the AVSys, what is for the end-to-end autonomous driving development uh, systems. So I know that in this session, everybody interesting in about the autonomous vehicle. So I want to introduce the design cycle of the autonomous driving systems. As you can see, like the Waymo, the Google autonomous car, uh, for developing this vehicle, you need to do the plan and the design for the system, and there is an actual implementation, and finally there's the test and the integration stage. So usually this cycle is called as the V cycle, because when you scoop down, the testing is matched to the planning and design cycle. As you can see, like this. If you go down to the implementation stage, if you find some bug from the module, then you need to go back to the design cycle. And if you had found some system fault, you need to go back to the system design stage. So this cycle is too painful if you find some error at the final stage of the testing or integration. Uh, and, but the system design tools like AutoSAR or Electrovit or Vector, uh, they doesn't cover about the design time validation, like simulation or the parallel resource utilization. Uh, the autonomous vehicle system is have to be the real-time system. What is the real-time system? It means that uh, this is system need to uh, we need to uh, ensure the deadline. Uh, Obviously, like the vehicle, if not activate the brake within the certain of time, then the car could be a crash. So for this, uh, the real-time system have the period and execution time and the deadline. And if you do not manage this the real-time system well, then you need to you could be very strategic uh, the accident. So, uh, but the actually the ideal uh, design system and the actual the implementation is not same. Uh, on the left side, uh, if you think the system will be stable in the design phase, but actual implementation is not uh, stable because there is a sensor suite and some computing unit and some the target vehicle does not integrate it well, then the system is not will be stable. So and obviously the commercial system design tools doesn't doesn't care much about the resource utilization yet. So for ABCs, they cover the also the system design and code generation for the end-to-end tool chain, and also we cover the design time validation and optimal real-time scheduling. Uh, As you can see, the simulation result in the left side, we offer the correct design time validation, which means the simulation result is very similar with the real uh, actual behavior. And the right side, the optimal parallel resource utilization, we develop our own research results, so it can cover up the utilization of the real-time tasks. I'll introduce about these systems. And for these, the AVSys and end-to-end tool chain, there is some stage like system design and design time validation and code generation. And each stage has three steps. First one, implementation goal. And second, the AVs cover the end-to-end tool chain. And third, there is output of our AVSys systems. And step by step, first one, the system design. Uh, for the implementation goal, usually the autonomous driving system is run on the ROS, which means the robot operating system. And the ROS is consists of uh, the nodes and edges, which can be presented as the DAG, the direct acyclic graphic. So as you can see, so for example, the rain detection. For the rain detection, first the camera should observe the image, and after that there is some image processing, and at the bottom of each node there is some execution time and the period for each node should be uh, satisfied. And after the image processing, the perception is going on, the lane detection. After that, the lane detection gives the model speed and some the angle of the vehicle. Then finally, the the vehicle driver actuate the signals. So this is the DAC representation of the lane detection example. So this is the implementation goal. We want to make this some module of the autonomous vehicle driving systems. Then AVSys cover this IDE system. Uh, as you can see, the left side, there is the block diagram. So we utilize the graphic model framework of the Eclipse and also some Eclipse modeling framework. So you can implement the node and edges with these classes and the properties. And also for the real-time validation, you need to type in the real-time parameter configuration. As you can see, the scheduler, the offset, and period, and deadline, and some execution time for this each node. Then we cover the simulation of the timing behavior. After you draw this block diagram, then you can get the portable system design markup. As you can see, the XML usually. So, which means portable. It can be adapt to the various target systems, like some PX2 or TX2 NVIDIA board and the raw system, or the Infineon CPU with the AutoSol system. And this was the system design stage. The second one is the design time validation. Uh, we want to make end-to-end tool chain, and we want to do the system validation in the design time. So we just simulate in right after the system design. So the first implementation goal is the actual behavior is same with the simulated behavior. This is called the functional and temporal correct simulation, which means functional correct is the module execute the right uh, result. And also the temporal correctness means the release and execution and uh, the final execution time is same with the actual behavior. So we want to test this temporal behavior. For that, just you need to type the processor number and some GPU number for the simulation. That's all. For all each node, you need to type some system environment configuration. Then we cover the simulation part. As you can see, the output of the ECU, temporal behavior, or some memory dynamics. You can simulate the resource utilization, as you can see. And the final stage is code generation. Uh, these are the implementation goals. We have several target architecture like the the NVIDIA board and the ROS or some Infineon and the AutoSAR. Then you just need to configure the target systems. What board are you using it, and the midware, which version you need to operate. And after that, you just click the run button. Then it will create the target code for the target system. Uh, as you can see, usually the ROS output is the package of the ROS system. And you can run this code on the simulation car or the commercial car or some RC cars and so on. So the stages are for the end-to-end tool chain and system time validation. And some more, you can do the optimal real-time scheduling. Same with the end-to-end tool chain, but there is some focus on for the optimal real-time scheduling. First, in the system design stage, if you configure the parallelization for these nodes, each node, like what processor are you using it, and what's the max parallelization, if you type this information, then the AVC system cover this parallelization. Uh, Before talking about the optimal parallelization, I want to talk about what is the parallelization. Parallelization is the parallelization framework supports that each task can be parallelized as the prefix number. And there is a pros and cons for the parallelization. If you do the parallelization, then uh, you can you cannot violate that parallelized task, but it can interfere other tasks with the parallelized tasks. So uh, what what that mean the pros and cons? If you do some task parallelized, then the task can be executed more, but the other task can be interfered by that parallelized task. So the the optimal number of the parallelization assignment is very uh, hard because it's the time order is the NP hard problem. So we want to do this optimal parallelization in the polynomial time. This is our the research result. So this is the implementation goal. If you type some uh, parallelization the configuration, then we do the optimal parallelization for its target system. So these are the results. As you can see, we uh, proposed some the papers in the ARTAS or TC or RTSS we can get the double more scheduling for the real-time task, or in the 50% upward for the task utilization with this optimal parallelization uh, yeah, method. And also, the AVSys has some broad spectrum. Uh, for the target system, you can use the simulated car like car sim and RC car. In the remote lab, we have the T-Rex F110, and also we implemented the Ionic car in for the commercial cars, and also the computing unit are broad like PC or NVIDIA board or some ECU like Infineon RX, and we the ABCs is open for the beginners. Like we have the remote lab uh, who does not have the commercial car for all the sensor suit can use this remote lab. Uh, in the AVSys, there is some remote login and file transfer system. And if you log in there, then you can download the package of the module what you created through the AVSys. And after that, you can run these codes on the remote RAM. So you can see the uh, actual the behavior of the car through the camera, and it can be yeah get some the logs and debug information for that. So these are the introduce for the our autonomous vehicle driving system development IDE, AVSys. So please join us. We have a open source project in the Eclipse Foundation, and also we have a GitHub to code, so you can download the test for the IDE. Or the in front of this slide, those are our vision and ongoing projects. So it does not cover all the stuff I showed you, but we develop with other contributors. So if you have an interest in the IDE of the autonomous vehicle driving system, uh, then join us. You can find the information all of this on these websites. Yep. Thank you for listening. And any questions? Uh, no, it should be public, but uh, okay. Uh, I will check through later, but it will be able after that. Yeah. Actually, uh, for the real-time behavior, we use some uh, the frameworks like the OpenCL and OpenGL stuff, OpenCV like stuff. So it can use the parallelization source, and after that, the Linux that gives some attribute for the real-time stuff like the deadline. RT Linux cover that stuff. So yes. Mm-hmm. Mm, yes, that's the hard part because uh, for supporting all the hardware system, we have to support all the configuration of the each hardware. So that is the hard part of this open source project. But we started from the some RC car and the Ioniq of Hyundai, and we want to cover the more hardware system with with the contributors. So for now, we doesn't have a that much various all the hardware system. Yeah. Oh yeah, we tried it. We trying it with this IDE. So. Uh, cause for now they just use the ECU, not the CPU and GPU. They just using the ECU for now, but they can be used the TX or a TX2 or PX2. Then we can use our some module for those target board, uh, and we try to use this that the the car the hardware. Uh, yeah. Oh. For the simulation, actually, uh, they they doesn't cover that because there's some yeah actual simulation. They observe the real hardware behavior. After that, using that data, we do the simulation. So for the right simulation, we need the actual the hardware system. And yeah, using that trace. Yeah, yeah. And any more? Mm, uh, I'm not uh, doing those stuff, but in my limited information, we do some support for the open PL and open CV stuff. But if those framework can support some parallelization with some kind of constraint, then our system can support those tasks. I think the constraint is depends on the frameworks of the like OpenCL and OpenCV. For that, if uh, actually the parallelization constraint is depends on the or the overhead and the uh, how can be reduce the execution time of the longest one. So it's yeah how yeah makes sense. Also, if the overhead of the parallelization is too high, then the parallelization is not that working well. So those it depends on the tasks, the overhead, and the systems. So yeah, those can be the one constraints. Okay. Uh, not yet. So mm, yeah, of course. Yeah, but I'm not the decider of this project. But okay, then let's. Oh yeah, thank you for listening, everybody.